All right, so in this video, we're going to define a couple of things here. So the first one is the rank of a matrix. So we're going to introduce two new vocab terms to describe a matrix. The first one is what we're going to call the rank. So the rank of a matrix, which we'll use the symbol R of A, is equal to the dimension of the column space of A. All right. And the other term we're going to look at is the nullity of a matrix, right? Which we'll look at N of A. And what that is going to refer to is the dimension of the null space of A. Okay. All right. You can instantly determine the rank and nullity when we're in reduced row echelon form, right? It should be obvious there what those values are going to be, right? Because when it's in reduced row echelon form, right, the number of pivot columns tells you which column vectors form the dimension for the column space. Right, and then the free variables tells you, well, the size of now we know, right, it's the dimension of the null space, right, how many linearly independent vectors there are in a basis for the null space. Right, so for example here, let's take a look at this matrix. So we have the matrix 1, 2, 0, 1, 3, and 0, 1, 2, 1, 1. And 2, 5, 2, 3, 7. All right. And then we reduce row echelon form RREF. And this here reduces to the matrix okay, and then from here we see, all right, well, if we were having the column space, we could say, all right, the column space here is equal to the span. We have two linearly independent sets, the span of 1, 0, 2 and 2, 1, 5. Okay, and we can see that the basis consists of two vectors. So the dimension of the column space of A is 2, or in other words, the rank of A is 2. All right, and then we could see here if we wanted to find the null space, right? Again, null space is the solution to the homogeneous system, right? So if we have this x1, x2, x5, we see we have three free variables, x3, x4, x5, right? So those are going to consist of our our elements in our null space, because I can write x1 as, can be written as 4 x3 plus x4 minus x5. And then x2 can be written as, so this is our solution to our homogeneous system, negative 2x3 minus x4 minus x5. All right, so our null space of A would be x3, any linear combination that looks like this. So x3 would be here 4, 0, 1, 0, 0. Here x4, that's 1, negative 2. Here and x4 here, 0, 1, 0, plus x5. So it'll just be a linear combination of these vectors here, -1, -1, 0, 0, 1. Right, where x1, excuse me, x3, x4, and x5 are just any real numbers here. Right, we could see that here the dimension are these 3 vectors here. So the dimension of the null space of A is 3. All right, or in other words, the nullity of A is 3. All right. Okay. All right, now here, what this is kind of now lead us to, we could see we're limited into what the size of the column space and the null space can be, right, by the number of columns, right? So if you look here, right, at most we could have the most pivots for this matrix would be 3, right, because of the number of rows, and that would mean that we would be, that would also limit the size of the null space, right? So in general, what we could say here about the size of the matrix and the nullity and the rank, if A is n by n, then the rank of A plus the nullity of A is equal to n. All right, and if we look at our previous example, we had a 3 by 5 matrix, right? Where this is our m, this is my n. All right. All right, so in our previous example, that our n was 5, and we did find the dimension of the column space of A was 2, and the dimension of the null space of A was 3. And again, 3 plus 2 is 5, which is the number of columns. All right. And that had to be the case, right? It can't be any more and it can't be any less, right? Because if we max out on the column space, at most there could be 3, right? And that would leave that the other 2 columns would have to be the free variables, right? So this is just our constraint for every matrix, right? That's how the rows and the columns are working together in the sense to determine the column space and the null space. All right. Okay. So now this brings us to our conclusion here of this section when we want to look at square matrices. And again, we want to focus on non-singular and singular matrices and what that tells us about now the rank and the nullity. Right? So for any square matrix n, right, we can now add to our NME theorem. We're now at round 6, right? Because think if our square matrix n, let's say that A is non-singular. Right, so that means here we have our matrix A, right? It's non-singular, right? Whatever this looks like in here, right, has any number of elements here, n by n. Right, so there are n columns, n rows. Right, so if it is non-singular, that means that when I reduce row echelon, right, then this reduces to the identity matrix, right, IN. Right, but in other words, what that's telling me is that I have n linearly independent columns, right? In other words, that the dimensions of the column space of A would be equal to n. All right, and then furthermore, it's not going to violate the previous theorem, the rank plus nullity, is the columns, right? Because the null space of A, right? What I know of a non-singular matrix is simply the zero vector. Right. Now the dimension of of a vector space like this or of a set like this is 0. So we define the dimension of the null space of A here is 0. All right. So if a set just contains the 0 vector, right, we call the dimension 0, and it's still n plus 0 is still n. Right. So it still holds that the rank plus nullity is the columns. So now this is almost directly, right, we can add to our theorem, our NME6. So in round 6, now we can add these following two conditions. Okay, so from our textbook here. Okay, so before we've up to 1 through 8 here. We've had those from previous sections, and now the last two come from this section here, where the rank of A is n if it's non-singular, right? Because row reduces to in, and the nullity of A is 0 since it only contains the 0 vector. So now we can add to our list here. We're up to 10 equivalent statements, right, where all of these means the same thing, right? If I know one of these is true, the other 9 are also true as well.